Hello students, welcome to the GATEvantage Series. So today we are going to discuss about signals and systems. Right, so October month, we are in the October month, right? So I think GATE 22 students, you might be a little pressurized. It is not easy in the month of October, by the way. There are a lot of things to cover. Probably so many of you are in a syllabus completion mode and thinking about how to do the full revision of the subjects. Few people might also have confusion regarding when to start test series, right? So all these things are occupied in your mind. But what does a sincere student do? A sincere student thinks that I'll cover everything, right? Sincere students think that I'll cover everything. Whatever is a part of the GATE syllabus, I'll cover everything in a hope that I'll get 100 marks or in a hope that I'll get maximum marks. Rather, what a smart student does. A smart student focuses on the things which are more important. And this approach is very much required in the GATE examination. If you are preparing for the GATE examination, you have to be smart in your approach. Because it is not about one subject, isn't it? It is not about covering single subject. There are at least 10 to 12 subjects in your curriculum. It requires to understand what are the most important things as far as your syllabus is concerned, as far as any subject is concerned for that matter. And then prioritize the importance, do the problem solving on the concepts which are very, very important, and the concepts which are not much important, hardly the question comes from it. So you just have a basic idea about those concepts. This is how you have to prepare for the GATE examination. In today's session, we are going to cover signals and systems, one of the most important topic, that is system properties. We're going to cover system properties, which is one of the most important concepts of signals and systems. This is also considered to be one of the basic topic. And tomorrow's session we're going to cover the concept of convolution, which is full of shortcuts and tricks that is exactly going to be there at the same time, that is 8 p.m. tomorrow. Okay, so let us not talk about tomorrow, let us focus upon today. Okay, let us focus upon the today's topic, that is system properties. So whenever we talk about a system properties, first of all you should have an understanding about what is a system, isn't it? Before you talk about the properties of the system, you should have an overall understanding about what is a system. So can my dear students define for me what is a system? Don't worry, we'll try to cover as many problems as possible. We'll try to cover whatever is required for the GATE examination as far as this topic of system properties is concerned. So don't worry about it. Let us go from the very basic part to the requirement of the examination. So can you please define what is a system? Let's see who all are the part of the session. I have Revati, I have Harsha, I have Ranjit. Okay, what about the other students? What about the other students? Good evening, all of you. Please comment in the chat box, everyone. Everyone who is a part of the session, please comment in the chat box. Looks like only 3 students are interested, huh? What about the other students, my dear students? Come on. Can you define a system for me? Can you define a system for me? Yes? Come on. System. Yes, we have Avinash, we have Amir, we have Amartya, we have Harsha. Aniket, love you too. Yes. Okay, so Harsha says that which takes some input and operates some operation and give the output. Very good. Group of members, okay. So we say, we don't like the system in India. We don't like system in India, how the government works. The system in India is very bad, we say, right? So that's why Harshita is saying that group of members, which gives specific output for a given input. Okay, good try, good. Amir? Pujari says system is a set of components which performs a particular action. Good, very good. The easiest of the definition, which receives input and gives the output. Which receives input and gives the output. Right? Absolutely yes. Everyone is correct. Everyone is correct. See, it doesn't matter what the textbook definition is. The understanding is very, very important, right? The understanding is very, very important, and I really appreciate all of your understanding. So when we call a system, of course we have an input or inputs. We have an input or inputs, multiple inputs. So we have an input, and the system processes the input, or a system manipulates the input to give an output, right? To give an output. And generally this output is going to be a desired output, right? Generally this output is going to be a desired output. For example, if you are attending this session, you want some output which is desired, isn't it? You want the output which is desired. Probably you are aiming for having more number of marks with the help of this GATEvantage series. There is some reason why you are attending it. Right? So you want a desired output. What is the input? The energy that I am putting, and also the attentiveness that you are putting. All these things contribute to a desired output. So we have an output which is desired. So come again. So a system is going to manipulate or process the input to give the desired output. What is that? It gives you the desired output. Right? Yes or no? The system processes the input to give the desired output. So now, if you are getting a desired output, there is an organized way of presenting a system, isn't it? The system has to be organized. For example, if I am delivering a lecture here, I have to go from a very basic level to a level which is required in the examination. And we have to cover each and every model of the question. In the same way, when you are building a system, when you are designing a system, it is required that you have to keep it organized. You have to arrange it in a more meaningful manner. We have to arrange it in a more meaningful manner, right? So we can say a system is a meaningful interconnection of devices. A system is a meaningful interconnection of devices. We can say the system is a meaningful interconnection of devices. Okay, you cannot, just connect a few pieces of things and say this is my system. It should be meaningfully connected. It should be meaningfully connected. So meaningful interconnection of devices contributes to a system. That will be control system. Only a system gives desired or not as well. See, what happens in the case of a control system is you are trying to control the output. That is the reason why we are calling it as a control system. But whenever you are talking about a system, whenever you are using a word called as a system, it means that you are expecting something out. For example, you have a digestive system. Okay, you cannot have a digestive system just functioning just like that. Or I'll do whatever I want. No. Then we will not call it as a system. The moment you are calling it as a system, it means that it is going to give you something which is desired. Now, if you wanted to control it, if you wanted to have a control over the output, then we use something called as a control system. Are you able to understand? Yes or no? Right? So system is something which is a meaningful interconnection of devices. It gives you an output. Which is nothing but a processed version of input. Okay. Now, when we have a system, so I think Harsha has already told control system. there is a communication system. There are different types of system. I already told you the digestive system. These are all different types of systems having different purposes, Now, what is common for everything is that you have to understand the properties of the system, and that is where GATE focuses on. That you should not understand different properties of the system. There are 6 very, very important properties. What are they? Now we will go one by one. So we will start with something called as a static system. And a dynamic system. So this is based upon which property? Can you please tell me? When I have a classification of a static system and a dynamic system, it is based upon what property? On what basis do we classify the system as a static system and a dynamic system? On what basis do we classify the system as a static and dynamic? Who is going to respond? Can I have the responses? On what basis do we do this classification? Come on, yaar. This is a very basic question. Yes, Amartya, absolutely correct. Very good, Amar. That's an excellent answer from Amir, Pujari, everyone. Yes, it is based upon the memory. We classify the system as a static and a dynamic system. The second one is invertible, non-invertible system. Invertible, non-invertible system. Can anyone give me an example of an invertible, non-invertible system? Can anyone give me an example of let us give an example of an invertible system. Who is going to give me an example of an invertible system? Very good, Harshita. Very good, Hemant. Good response. Come on. Invertible system. Do we understand what is invertible? What is the expectation? When we call a certain system is a invertible system? When we call a certain system as an invertible system, then what is the expectation that we have in our mind? Yes, very good, Amartya. One-to-one mapping. My expectation is that if I have a system for which I am giving an input and the system gives me an output. Now, from this output, whatever output I'm having, can I once again get back my input? Are you able to understand? Yes, I have transformed my input to output. Now, is it possible that I can process my output to get back the input? Is it possible that I can process my output to get back the input? This is more similar to the top. In your childhood, you might have heard about something called as a reversible reaction, irreversible reaction, right? You might have heard about a reversible reaction and irreversible reaction, yes or no? It is similar to that. From output, if you are able to get back your input by different processing, then we call the first operation, the operation of converting the input to output. The operation of converting the input to output as an invertible operation. For example, if you are talking about pure amplification. So the exact opposite of amplification is nothing but attenuation. Now you will say, sir, differentiator integrator, square under root. But wait, there are a few more things that we have to discuss. Okay, we cannot directly say like that. But the intent is that. What is the intent? When I say something as an invertible or a non-invertible system, so what I'm expecting from an invertible system is that, I am processing my input to get an output. Now, is it possible that from my output, I can get back my input? Can I do any transformation on this output to get back my input? Then the first operation that I've performed to convert the input to output is what we call as a invertible operation. That is the second one. Okay. We will see the problems. Okay, one by one we'll see all the problems. So causal, non-causal. So this comes from the property called as causality. This comes from the property called as causality. So what do we understand by causal system? What do we understand by causal system? Anyone? What do we understand by causal system? Yeah. So there is a link from one of our moderator giving the GATEvantage series schedule. See, definitely GATEvantage series is going to be very, very helpful for the students because, as I told, you have to focus on the pattern. And GATEvantage series is going to promote you to focus on the pattern. What is important, what is not. Focus more on the important topics and less on not so important topics. This is very, very important in the examination point of view, even though we are targeting few topics from a set of subjects. Now we are encouraging you to come up with more number of topics from a particular subject, right? So yes, causal means depend on present and previous. So causal system means it depends upon present and previous time. This is what Pradeep is saying. Amir says that present output depends upon present input. Okay. Right, respond on depend upon past and the present input. Past and the present input. Good, okay. So causal, cause effect. There is some reason why something is happening. If something has happened, there should be some reason behind it. There should be some cause behind it. Okay, so the word causal comes from the word called as cause. Okay, so if you are getting an input, if you are getting an output, the output is because of the inputs. Now what kind of relation do we have between the output and the input? What kind of relation do we have between an output and an input? So generally, if you think about it, your output depends upon the present input, right? So whatever input you are giving, based upon that you will get an output, present input. And the output can also depend upon the past input. So if, for example, if you are pushing me, then because you are giving me an input like this, I am falling. Or there are a series of people who are pushing me, I am falling down, right? But let us say tomorrow someone is going to push me. Tomorrow someone is going to push me and I am falling now itself. Is it causal? Tomorrow someone is going to push me, now I am falling down. Is it causal? No. Right? So causal means your output can depend upon present and past. The output can depend upon present and past, but it cannot depend upon the future input. So is it possible that, okay, I am saying that a causal system is a system which is depending upon present and past inputs. Is that sufficient? This is a very incomplete definition. I should say, okay, it can depend upon present and past inputs, but it should not depend upon the future. It should not depend upon the future inputs. It should not depend upon the future inputs. So that completes the definition of causal. Your understanding is correct that a causal system can depend upon present and past input, but you should also add one more thing, that it should not depend upon the future input. It should not depend upon the future input. If it starts depending on the future input, I told you, right, tomorrow someone is going to push, I am falling now itself. If this happens, then we call the system as a non-causal system. Next one is stable. Everyone wants to be stable, right? Everyone wants to be stable. You are asking a small question and you expect an answer from me. If you are asking a small question, if I shout, what is this? Then probably you think something is wrong with Santhosh sir. Huh? You will think that something is wrong with Santhosh sir, right? Yes or no? So if you are asking a simple question, I have to give a simple answer, right? If you are asking me a simple question, I have to give you a simple answer. I can't shout on you, right? The moment I start shouting on you, then you will think there is something wrong with Santhosh sir, right? Right? So stability is something which is related to this. Stability is something which is related to this. Next one is about time variant and time invariant. So can anyone define for me what is a time invariant system? When I say a system is a time invariant system, when I say a system is a time invariant system, what do I expect from the system? Many people say, many students say that sir, output should not change with time. Output should not change with time, that is an invertible system. How many of you agree to this definition? Time invariant. Something should not change with time. Either input should not change with time or output should not change with time. What is exactly correct? What is exactly correct? Who is going to respond? Yeah. System parameters will not change with respect to time. Absolutely correct. Absolutely correct. Wonderful answer. It is the system's behavior or the system's parameters which should not change with time. So, sir, what is the system parameter? What is a system parameter? Very simple. Let us say I am teaching the class for 2 to 3 hours. When you are just starting your class, right? When you are just starting your class, then you are very fresh, right? So many things to learn. You will completely focus on the class, hopefully. But as soon as the 2 hours is completed, then I teach anything new, then you say, no, sir, sufficient. Aaj ke liye sufficient hai, huh? What is happening basically? What is happening? Simply, your behavior is going to change with respect to time. The freshness with which you have entered the class, when you are going out, you are not going out with the same freshness, isn't it? Your behavior is changing. This is a time variant behavior. This is a time variant behavior. If you remain equally fresh from the start of the class to the end of the class, if you remain equally fresh, then your behavior is going to be a time invariant. Now, when I say any system is a time invariant system, any system is a time invariant system, it means that its behavior should not change with time. We are not putting any constraints on the input, nor we are putting any constraints on the output. We are not putting any constraints on the input, we are not putting any constraints on the output. Output can change with respect to time. Many people think that output will not change with respect to time in the case of time invariant system. Wrong. No, not correct. Outputs can change with respect to time. Input can change with respect to time. But what should not change with the time is nothing but the system behavior. And you have the same expectation on me also. You want me to carry the same energy from start to end, yes or no? You want me to carry the same energy from start to end. Probably I also have a similar expectation from you. Initially you are very eager to interact, but slowly and slowly the energy reduces. Yes? Right? So if it does not reduce, if you are equally fresh, then you are a time invariant system. Then you are a time invariant system. Yes, Amartya, yes. Characteristic of the system does not change with time. And the last property is a linear property. So linear means you expect the superposition principle to be satisfied, which is a very simple definition. For example, if you are putting a 1 rupee and you are getting a 1 chocolate, then if you put 10 rupees, then you are expecting 10 chocolates. As simple as that. That is what we are calling as a linear system. If I put 1 rupee, I get 1 chocolate. If I put 10 rupees, I am getting 5 chocolates. Then there is something problem, right? This is a non-linear response. This is a non-linear response. Ideally, I would be requiring a linear response. Ideally, I would be requiring a time invariant response, right? Now, all these things that we have discussed till now, is only about our understanding. Yes, understanding is very much required for the GATE examination, but along with that, if you are able to express all your feelings, if you are able to express in terms of mathematics, then you can solve as many number of problems in the GATE examination. It is what we are calling as an application. You have an understanding, now can you apply onto the different problems? That is what is required in the GATE examination. That is what is required in the GATE examination. Now, let us try to put it in a mathematical terms. Whatever understanding we had till now, we will put in a mathematical terms. We will see how the GATE questions are asked, and lastly, we will play the live quiz. Okay, where whatever understanding you have, whatever problems you have solved, then at the end of the session, you can test yourself how much you have understood. It is not for me. You are not going to give live quiz for me. Okay, you are going to give a live quiz for yourself. It is for your benefit. It is more like a warm-up. Okay, before you go into the GATE examination, before you write all the kind of test series, before you go for all kind of test series, this is a simple warm-up. Whether you have understood the concept, whether you are able to apply the problem solving on your own. Thanks a lot, MSP Ready. Thanks a lot. So now let us start, my dear students. Let us start. Okay, the first property is about the memory, right? Yes or no? The first property is about the memory. If your system is having the memory, are we going to call it as a static system or a dynamic system? If your system is having the memory, do we call it as a static system or a dynamic system? When the system has a memory, then the system is going to be dynamic. Right? Yes or no? If the system is having a memory, then it is going to be dynamic. If the system does not have memory, then it is what we call as a static system. Now, how do you call yourself as? Are you going to call yourself as a static system or a dynamic system? Really? Are you a dynamic system? When you start writing the examinations, when you start writing the tests, you're not able to recollect the formula. Arey yaar, what happened? Then suddenly your behavior changes to static, huh? Right? So our behavior fluctuates between, of course, capability wise, no doubt you are a dynamic system. Capability wise, no doubt you are a dynamic system. But approach wise sometimes, right? Approach wise sometimes we transiate between a static response and a dynamic response. A static response and a dynamic response, right? Especially in the examinations. Especially when it comes to tests. Probably not with respect to a cricket match. Probably not with respect to a movie. But with respect to examination for sure. That we fluctuate between that of the static and the dynamic response, right? Yes or no? Right? So system has a memory. We call it as a dynamic system. No memory. Static system, isn't it? If it is not having any memory, then we call it as a static system. Let me have a circuit like this. Many people might be wondering, where are my gate problems? Sir, by now it's already half an hour. You should have started solving gate problems. What are you doing? We'll come to the gate problems slowly, okay? We'll come, for sure. Can you please tell me? Can you please tell me whether it's a static system or a dynamic system? This is my system, isn't it? You have an input, you have an output. Is it a static system or a dynamic system? Is it a static system or a dynamic system? This is an example of a dynamic system. This is an example of a dynamic system. Why, sir? Why? Why is it a dynamic system? It is a dynamic system because of the fact that you have a capacitor. Very good. Very good, Pradeep. It is because you have a capacitor. Very good, Harsha. It's because of the capacitor, because capacitor is a energy storage devices. Capacitor is a energy storage device. It can store something. It can accumulate something. It can accumulate the charges. It means that by default it is going to have memory. It means that by default it is going to have a memory. It's a storage element, isn't it? That is the reason why this system is going to become a dynamic system. Let me say y of n is equal to x of n minus 1. Very simple question. Y of n is equal to x of n minus 1. Is this system a static system or a dynamic system? Is this system, come on, is this system a static system or a dynamic system? Thank you, Harshita. Yeah. Is it a static system or a dynamic system? Come on, students. Y of 0, if I put n equal to 0. We are coming slowly into the mathematical terms, right? We are coming slowly into the mathematical terms, right? N is equal to 0, y of 0 is equal to x of minus 1. My dear students, y of 0 is equal to x of minus 1. What is it? It's a dynamic system. Why, sir? Because the output at n equal to 0, the output at n equal to 0 is depending on input at n equal to minus 1. The output at n equal to 0 is depending on input at n equal to minus 1. It means that there is a dependency on the past input. There is a dependency on the past input. The moment it starts depending on the past input, we call it as a dynamic system, because if you wanted to have a dependency on past, you have to store the past values. You have to store the past values. You have to recollect something. It means that it is a dynamic system. It means that it is a dynamic system. It means that it is a dynamic system because of the dependency of the past input. The output has a dependency on the past input. That's why we are calling it as a dynamic system. That's why we are calling it as a dynamic system. Clear, everyone? Is that clear to all of you? Yes or no? Is that clear to all of you? Y of t is equal to x of t minus 2 x square t. Y of t is equal to x of t minus 2 x square t. What is this? Y of 0 is equal to x of 0 minus 2 x square of 0. Y of 0 is equal to x of 0 minus 2 x square of 0. The present output at n equal to 0 depends on the present input x of 0. The present output at n equal to 0 or t equal to 0 for that matter depends upon what? It depends upon the input at t equal to 0. It means the present output depends on the present input. The present output depends on the present input. Yes or no? So we call it as a static system. We call it as a static system. We call it as a static system. Clear, everyone? Clear, everyone? You know how the gate questions are asked? I'm sure you are aware of it. How the gate questions are asked? Generally, the gate questions are not based upon a single property. Very rarely you will see that the gate question is based upon a single property. They will give you a relation between input and output. They will give you a relation between input and output and ask you whether the system is static, whether the system is linear, whether the system is time invariant. So the system, if you are confident one by one, definitely you will answer such questions. Right? Is that clear? So what we will do, we will take gate problems once we have a complete understanding of how to approach different characteristics. How to approach different characteristics. Once we have understanding of that, then we are very much ready for the gate problems. then we are very much ready for the gate problems. Now the next property is about the invertibility property, right? The next property is about the invertibility property. What did we discuss? Invertibility property, what did we discuss, my dear students? Invertibility means that whatever operation performed by the system, let us say that there is a system called as S1, which is giving, once the output is given, it is giving an output called as y of t. Once the input is given, it is giving an output called as, y of t. It is giving an output called as y of t. It means that you have processed the input to get an output. You have processed the input to get an output. Now, is it possible that you can transform this output to an input? Can you transform this output to an input? It means that whatever operation you are performing here, you are doing the inverse of it, right? If this is possible, it means that this operation that you have performed is an invertible operation. Okay, this operation is an invertible operation if you are able to get back your input. But if this operation is not an invertible operation, you have performed such an operation where it is impossible to get back your input. It is impossible to get back your input back. Why it is impossible, sir? Because you have performed such an operation here that once you get the output, it is impossible to get back the input. It is impossible to get back the input. Then we call this operation as an invertible operation if you are able to get back. If you are not able to get back, if you have performed such an operation where it is impossible to get back your input, then we call this operation as a non-invertible operation. We call it as a non-invertible operation. I mean, when I teach this invertible, non-invertible, I always relate my students with one of a movie clip I have seen. Okay, how many of you are from Andhra Pradesh? At least some of you watch Telugu movies, right? Okay, so there is one such instance. Everyone can relate to this. Probably it has happened to you also, right? Let us say you are standing on a weighing machine, right? You have in the railway stations, right? So you are standing on a weighing machine. You are standing on the weighing machine, and you are putting here a 1 rupee coin, expecting to get back the ticket, right? That small ticket which is having your weight. I don't know how much correctly it is going to give you a weight, but definitely besides the weight, it is going to give you some useful quotation, very good quotation. So if you are putting a rupee coin or a 2 rupee coin, now these days it is becoming costly and costly. Initially it used to be 1 rupee, then 2 rupees, now 5 rupees, right? Then you are expecting a ticket, but it is not getting. The ticket is not coming out. Then there is one of your friend. Array, this is not working for you. Your friend is standing now. He is putting a coin here. He is getting the ticket here. Now he puts back the ticket. He gets back the coin. How do you feel? You didn't get any ticket. He got the ticket. Not only that, he put back the ticket. He got the rupee coin back. This operation is a invertible operation, right? This operation is an invertible operation. We get a ticket, but is it possible that you put a ticket back and you get the rupee coin? Not possible. Generally, it is not possible, but sometimes it happens for few people, few lucky people. I'm not that lucky, right? Now, the intent is very clear, my dear students. The intent is very clear here. The intent is that you wanted to get back your input, right? You wanted to get back your input. For this, a very, very important thing has to be understood. For this, a very, very important thing has to be understood. If you are approaching it in the GATE examination point of view, you have to understand one very important thing. For the system to be invertible, it's a very, very important condition. Everyone, please be attentive. For system to be invertible, for the system to be invertible, there should be a one-to-one mapping between input and output. There should be a one-to-one mapping between an input and output. What do I mean by one-to-one mapping? If you are getting x of 0, x of n, I'm sorry. You're having 1, 2, 3, 4. Here you are getting A, B, C, D. Okay. So there should be a one-to-one mapping between input and output. There should be a one-to-one mapping between input and output. If you are having such a case, such a case where 1 is leading to A, 2 is also leading to A. 1 is leading to A and 2 is also leading to A, it means that one-to-one mapping is failing. Such system is a non-invertible system. Such system is a non-invertible system, because you are expecting that if you are giving A as the input again, you have to get back 1. You have to get back 1, right? So there should be a one-to-one mapping between input and output. There should be a one-to-one mapping between input and output. Is that clear, my dear students? There should be a one-to-one mapping between input and output. This is very, very important. This is very, very important, my dear students. Okay. Distinct output. So what we write generally is that distinct inputs lead to distinct outputs. Distinct inputs lead to distinct outputs. Distinct inputs lead to distinct outputs. Distinct input leads to distinct outputs. Is that clear? Thank you, Harshita. Thank you. Thanks a lot. This is a characteristic of an invertible system. This is a characteristic of an invertible system. For example, if I have a relation of y of t is equal to x square t. Y of t is equal to x square t, it means that I have an input called as x of t, I have an output called as y of t. If I give 1, I have 1 here. If I give 2 here, I have 4 here. If I give 3, I have 9 here. If I give 4, I have 16 here. But if I give minus 1, what am I having? If I give a minus 1, till here so far so good. Till here so far so good. But the moment I am giving minus 1, I am going to get back 1 again. I am going to get back 1 again. It means that 1 is leading to 1, minus 1 is also leading to 1. 1 is leading to 1, minus 1 is also leading to 1. It means this system is a non-invertible system. This system is a non-invertible system. This system is a non-invertible system. Is that clear, all of you, my dear students? Is that clear, all of you? Is that clear, all of you? Okay, so this system is a non-invertible system. This system is a non-invertible system. This system is a non-invertible system. What about, sir, let me have a y of t is equal to dx by dt. It's a derivative. So we generally think that, sir, derivation, integration. If I have derivative, opposite is integration. It is possible, right, sir? It is possible, but is it really? Please check here. X of t, y of t. If I give 1, it is 0. If I give 2, it is 0. If I give 3, it is 0. Because derivative of a constant, doesn't matter whether it is 1, 2 or 3, it is always going to be 0. Basically, derivative is going to kill the information. Derivative is going to kill the information, right? Okay. So this is the problem, my dear students. Okay. So whenever you are having a derivation or a derivative, it's a non-invertible system. If you are having such a system, where the input is x of t and the output is the derivative of it, such system is a non-invertible system. Such system is a non-invertible system because from this you can't ever get back your x of t. You can't ever get back your x of t. That is a problem, my dear students. That is a problem, right? So it is a non-invertible system because very simply there is no one-to-one mapping. Distinct inputs is leading to a same output. Distinct inputs is leading to a same output. That is the reason why it's a non-invertible system. That is the reason why it's a non-invertible system. Next. Come on. Next. What is that? Next we have something called as a causal and non-causal system. Causal and non-causal, right? We'll come to the gate problems, okay? Don't worry. Once you understand the concepts, we can very much easily do the problem solving. Causal and non-causal, I think we understood what is causal, non-causal, right? Yes or no? We have understood what is a causal, non-causal. Causal means it can depend upon the present, it can depend upon the past, but it cannot depend upon the future input. It cannot depend upon the future input. You remember? Because I mean you are pushing today, I can fall down instantly, or I can fall down after a second. But because of the fact that you are going to push me tomorrow, I can't fall now. This is against the cause and effect relation. This is against the cause and effect relation. Yes or no? So the definition of a causal system is that the output can depend upon the present and past inputs, but cannot depend upon the future input. Output can depend upon present and past, present inputs and past inputs, but not on future inputs. My dear students, this is very, very important. It cannot depend upon the future inputs. This is very important. Many of them know till here. Only some of them know this also. It should not depend upon the future inputs. It should not depend upon the future inputs. This is the definition of a what? This is the definition of a causal system. This is the definition of a causal system. Is that clear to all of you, yes or no? If you are liking the session, if you are feeling interested about the session, please don't forget to click on the like button and share with your friends. Okay? Come on. So this is about the causal system. Hold on. Sir, what you told is correct. No doubt about it. How is it possible to have a non-causal system? You told we agreed, right? You told we agreed that okay, the system is depending upon the present and past, it's not depending on the future. This is common sense, isn't it? This is common sense, isn't it? How can you have a concept on it? How can you have a concept on it, right? There are cases where common sense fails, but generally, is it possible? Do you really think it's possible? It's possible to have it is possible to have a non-causal system. Is it really possible to have a non-causal system, my dear students? Is it really possible? Any example? Can you give any example? Any example where it's a non-causal system? Any example where it is a non-causal system? Not the mathematical examples, okay? Not the mathematical examples. Physical examples. Physical examples. Physical examples. Sir, some of you might say, sir, I know what you are going to teach after causality. I know what you are going to teach after causality. You will teach about stability, right? You already know that. So it is possible, sir. But, because I have already discussed with you before in the introduction, that is the reason why you know. Many of the students take an example of a weather forecasting system. The moment I say predicting the future, or if I say depending on the future value, many people say or talk about weather forecasting system. Yeah, weather report. I mean, so India has a very good record of, failing of weather report. The day they say it's going to rain, it's not going to rain at all. It's not going to rain at all, right? So it means that it is a prediction, my dear students. Prediction on what? Prediction based on what? It is a prediction based upon things that have happened in the past. You are predicting the future. You are predicting the future. It might be wrong also, because you are predicting the future based upon present and the past. It can fail in few cases. Yeah, it is possible to have a non-causal system if your input, the input that you are giving is already recorded. The input that you have, if it is already recorded, then in that case it is possible. In that case it is possible. For example, you have a recorded class. I mean, some people are, too intelligent that they think that, sir, if it's a recorded session, I'll just jump, okay. That operation is a non-causal operation because you're having an access of what is happening in the future. You are having an access of what is happening in the future, but that is possible only when you're having a recorded input. So in case of recorded input, it is possible, but if it is a real-time input, then it is not possible to build up a non-causal system. It is not possible to build up a non-causal system. If you are having a recorded input, then it is possible to build up a non-causal system, because in the case of recorded, you have an excess of what is going to come next. Is that clear? So mathematically speaking, let us solve a problem. Y of t is equal to x of minus t. Y of t is equal to x of minus t. Y of t is equal to x of minus t. Can you please tell me what is this operation? Y of t is equal to x of minus t. If t is equal to 1, y of 1 is equal to x of minus 1. If t is equal to 2, y of 2 is equal to x of minus 2. If t is equal to 3, y of 3 is equal to x of minus 3. So if you see, this is 0, this is minus 1, minus 2, minus 3. Y of 1, the output at the instant of 1. The output at the instant of 1 is dependent on minus 1, which is a past value. In comparison to 1, minus 1 is a past value, isn't it? Similarly, y of 2 is depending on minus 2. Y of 3 is depending on minus 3, right? Yes or no? Okay, yes or no? It is depending on the past value. But the game is not over. If you take the t is equal to minus 1, then y of minus 1 is equal to x of 1. Y of minus 2 is equal to x of 2. Y of minus 3 is equal to x of 3. Now if you take the negative values of time, the output at t is equal to minus 1. The output at t is equal to minus 1 is dependent upon x of 1, which is a future input. The output at t is equal to minus 2. The output at the instance of t is equal to minus 2 is dependent upon x of 2. The output at t is equal to minus 3 is dependent upon x of 3. So this system is a non-causal system. Because of this. So my dear students, what is important in the examination point of view is that you try to find such an instance. Which makes it non-causal. If you are satisfied here itself, sir, see here, t is equal to 1 I am getting, t is equal to 2 I am getting, t is equal to 3 I am getting. So it is causal, sir. No. You have to look for such an input. That should be the approach. And if you are failing to get such an instance where it is depending on the future input, then you can call it as a, if you are not able to find any such instant where it is depending on the future, then you can call it as a causal. But in the examination point of view, you have to look for such an instant. You have to look for such an instant which makes it non-causal. Which makes it non-causal. If you fail, then we can call it as a causal. If you fail, then you can call it as a causal. That should be an approach in the examination point of view. Next example. Y of t is equal to x of t by 2. Y of t is equal to x of t by 2. So Harshita is saying that, sir, is there anyone from the other branches? So Harshita, which branch do you belong to, my dear? Which branch you belong to? Y of t is equal to x of t by 2. Y of t is equal to x of t by 2. Is it a causal system or a non-causal system? Is it a causal system or a non-causal system? Everyone. Is it a causal system or a non-causal system? Y of t is equal to x of t by 2. Is it a causal or a non-causal? Causal? T equal to 1, y of 1 is equal to x of 1 by 2, y of 2 is equal to x of 1, y of 3 is equal to x of 3 by 2, y of 4 is equal to x of 2. So again you draw this is 0. The output at 1 is depending upon 1 by 2. The output at 2 is depending upon 1. The output at 3 is dependent upon 3 by 2. 3 by 2 is somewhere here. It means that it is depending on the past. It is depending on the past. But you should not hold here itself. Let us put the negative numbers. Let us put the negative numbers, guys. Same approach. Let us put the negative number t equal to minus 1. Y of minus 1 is equal to x of minus 1 by 2. If this is minus 1, minus 1 by 2 is somewhere in the middle. Right? So minus 1, y of minus 1, the output at minus 1, is dependent upon the input at minus 1 by 2, which is a future input. Which is a future input. Okay, Harshita is from civil engineering. Probably you are at the wrong class, huh? You are at a wrong class. Probably you are enjoying this class. That's why you are sitting here, right? Yeah, you will be having civil engineering sessions. I think we are having the sessions of strength of materials, fluid mechanics, structure analysis. All these subjects we are going to have in the coming sessions. Okay. Please do follow the GATEvantage series. Probably this session is not very much useful for you because you belong to civil engineering. But definitely we are going to have more sessions which are related to civil engineering. Is that clear, my dear students? Did you understand why this is a non-causal system? Did you understand why it is a non-causal system, my dear students? Have you understood why it is a non-causal system? Yes or no? Have you understood that? Y of t is equal to x of t square. Y of t is equal to x of t square. Y of t is equal to x of t square. Simple. Y of 1 is x of 1. Y of 2 is x of 4. Y of 2 is x of 4. Right? Yes or no? Yes. So can you please tell me whether it is a causal or a non-causal? Straightforward non-causal, isn't it? 0, 2, 4. The output at t is equal to 2 is dependent upon the input of a t equal to 4. So it's a future input. My dear students. It's a future input. So the system is a non-causal system. The system is a non-causal system. The system is a non-causal system. Yes or no? Next. Next is about stable, unstable. Next is about stable and unstable. Now when you are learning about the concept of stable and unstable, the first thing you should know is what is the meaning of a bounded signal. First thing you should know is what you understand by a bounded signal. That's very, very important. So let me draw some figures. Can you call them whether they are bounded or not? Okay. Okay. So there is a signal like this. Is it bounded or not? Is it bounded or not? Is it bounded or not? A, B, C for you. A, B, C. Can you please tell me which is bounded, which is not? A, comma B, comma C, comma D. Which of them is bounded? Which of them is bounded? Thanks a lot. Harshita, thank you. Yep. Come on, my dear students. A, B, C, D. C is unbounded. Very good. That's the correct answer. That's the correct answer. C is unbounded. Correct. This is unbounded. No, someone says that C is bounded. Okay, fine. Fair enough. Now let me give you by what basis we are going to call the input is bounded or a signal is bounded. Whenever you are having a signal called as x of t, if the magnitude of this x of t, is less than infinite, it means in a very simple way, the amplitude or the magnitude has to be a finite value. At any point of time, if the magnitude or the amplitude, if it is a finite value, then we can call it as a bounded input or a bounded signal. Now by that logic, see, we are only looking at the amplitude, okay? We are only looking at the amplitude. Amplitude or magnitude, my dear students, okay? We are not looking at the x-axis because this is an independent variable. This can vary. No condition about this. What is required is this value. Is it touching infinite at any point of time? Here, no, it is not touching. It means that it is bounded. Here also, no, it is bounded. Here, as t tends to infinite, the x3 of t, the magnitude is tending towards infinite. As t is tending towards infinite, here it is tending towards infinite. So this is unbounded. Because as t tends to infinite, it is tending towards infinite. Okay, the signal is tending towards infinite. So this is unbounded. What about this? This is misleading. This is what we call as a unit impulse. Del of t. Del of t is equal to infinity for t equal to 0, and it is equal to 0 for t not equal to 0. This is what we learn in the preliminary classes. Of signals, that a unit impulse is going to have a value of infinite at t equal to 0, and it is equal to 0 for t not equal to 0. This is what we call as a unit impulse. Why are we calling it as a unit impulse? Because the area under the impulse is equal to 1. the area under the impulse is equal to 1. The area under the impulse is equal to 1. The area under the impulse is equal to 1. That's why we are calling it as a unit impulse. That's why we are calling it as a unit impulse. That's why we are calling it as a unit impulse. But if you see its magnitude is equal to infinity. So therefore, we call this as a unbounded. So it should be very, very careful. Okay, what you see here as 1, it's not its magnitude, it is area. What you see here is a 1, this is not its magnitude, it is its area. Please understand. Okay, this is misleading, huh? This is misleading. But if you talk about the magnitude, it's infinity. At t equal to 0. At t is equal to 0. Now we have understood about what is bounded. Simply, if the magnitude is finite value, we call it as a bounded input or a bounded signal. Now, when we talk about stability, our expectation is that, our expectation is very simple, my dear students. Our expectation is very simple. You give a bounded input and you take a bounded output. Right? Give and take. You give an input which is bounded, you will get an output which is bounded. So bounded input, if it is leading to bounded output, bounded input leads to a bounded output, then we call the system as a stable system. Is it okay if it is happening for one instance? You applied such an input which is bounded and you are getting such an output which is bounded. This is happening for one signal. But the moment you are applying the second signal, it is not happening. For one signal, bounded led to bounded. But for another signal, for the next signal, bounded led to unbounded. For the next signal, bounded led to unbounded. Will you accept that? Arey sir, first case it has satisfied. So let me call it as a stable system. No, you will not say that, right? You will say no, it has to satisfy for every case. You will say that it has to satisfy for every case. You will not take risk. You will not take risk, right? Yes or no? You will not take that risk. Even in one instance, even in one case, the boundedness lead to unboundedness. Even in one case, the boundedness led to unboundedness, you will still call the system to be an unstable system. You will still call the system to be an unstable system. So the definition here is that for each and every, this is not for single, it is for each and every bounded input, the output is required to be bounded. For each and every bounded input, the output is required to be bounded. Then we call the system to be a stable system. It is not for one input, it is not for two inputs. For each and every bounded input, the output has to be bounded in nature. The output has to be bounded in nature. Then only you can call it as a stable system. Then only you can call it as a stable system. Is that clear, all of my students? Is that clear, all my dear students? Yes or no? Let me take an example. Y of t is equal to e power x of t. Y of t is equal to e power x of t. Can you please tell me whether this system is a stable system or not? I think we understood what is a stable system, right? We understood what is a stable system. For each and every bounded input, the output has to be bounded in nature. For each and every bounded input, the output has to be bounded in nature. That is what we call as a stable system. Now, if you have something called as a y of t is equal to e power x of t, you have something called as a y of t is equal to e power x of t. Now, is this a stable system? Yes or no? Is this a stable system? Yes or no? How many of you say that it is a stable system? How many of you say that it is a stable system? Y of t is equal to e power x of t. So you give x of t and you give y of t. Let me say my x of t is 1. Here you have e power 1. Here you give 2. Here you have e power 2. Here you give 3. It is e power 3. Here you give 4. It is e power 4. Here you give 100, here you have e power 100. Is it not a bounded value? Whatever bounded input you are giving, the output is bounded in nature. E power 100 is a big value. E power 100 is a very big value as compared to the top 100, but still it is finite. It's a very big value, but it is still a finite value. But it is still a finite value. Because it is finite, we can call the system to be a stable system. Some of you say that, sir, I calculated this value, sir, in my calculator. Okay, I believe my calculator. I calculated this value. This is saying, sir, it is not saying anything. Okay, this is not, my calculator is not calculating it. So thereby it is an infinite value. That is a problem with your calculator, right? The calculator is only capable of doing a finite number of operations, right? This value is a finite value. Only thing is that your calculator is not able to calculate, right? It's a programmable one, so it is not programmed to calculate such a big value, right? So we know that this is a finite value. We know that it is a finite value, so thereby we call the system to be a stable system. We call the system to be a stable system. For every bounded input, the output is bounded in nature. For every bounded input, the output is bounded in nature. Let me say y of t is equal to d by dt of x of t. D by dt of x of t. Y of t is equal to d by dt of x of t. Can anyone tell me whether the system is a stable system or not? Y of t is equal to d by dt of x of t. Y of t is equal to d by dt of x of t. The second one, can you tell me whether it's a stable system or not? Whether it's a stable system or not, yes or no? Whether it's a stable system or not? Y of t is equal to d by dt of x of t, whether it's a stable system or not, yes or no? Whether it's a stable system or not? Acha, tell me one thing. In this example, can I give infinity as an input? Can I give infinity as an input? Can I give infinity as an input here? No, right? Why, sir? I can't give this because I have to apply an input which is bounded in nature. I have to apply an input which is bounded in nature, yes or no? I have to apply an input which is bounded in nature. Can I apply here x of t is equal to t? Can I keep x of t is equal to t? If I keep x of t is equal to t, then I'll get e power t here. I mean, e power t is something like this, right? I'm sorry. E power t is something like this, right? Arey sir, you missed this. How can you miss this, sir? You're giving t, you're getting e power t. Hello, is this t a bounded input? Do you think this t is a bounded input? What is the meaning of x of t is equal to t? What is the meaning of x of t is equal to t? This, isn't it? Now here also this is going towards infinity. Here also it is going towards infinity. My dear students, please note this. So I can't give this also. Okay, many students ask the same question, okay. Why can't I give t here? Because t is an unbounded input. Because t is an unbounded input, I can't give this. Here in this case, can you please tell me whether this system is a stable system or not? Whether this system is a stable system or not? Yes or no? Whether this system is a stable system or not? Yes or no? No, very good. Because if you give the input as the step input, can you please tell me what is the differentiation of a step input? What is the differentiation of a step input? Can anyone tell me? Can anyone tell me what is the differentiation of a step input? Yes. What is the differentiation of a step input? Come on, it's a very basic question. What is the differentiation of a step input, my dear students? The differentiation of a step input is nothing but the impulse. The differentiation of a step input is nothing but an impulse. The differentiation of a ramp input is nothing but a step input. These are the basic concepts, my dear students. These are the basic concepts, and you are expected to know these basic concepts. This is not only useful in the case of signals and systems, it is also useful in the case of control systems. So here, can I apply step? Is it a bounded input, my dear students? If I give a step here, is it a bounded input? Yes or no? Is it a bounded input, my dear students? Yes or no? Can I call it as a bounded input? U of t, come on. U of t is something like this, isn't it? U of t is something like this. Can I call it as a bounded input? Can I call it as a bounded input, my dear students? Definitely yes. Definitely yes. It is a bounded input. So I am getting an output which is del of t. We have already seen del of t, isn't it? We have already seen del of t. Del of t is equal to infinite for t equal to 0. Del of t is equal to infinite for t equal to 0, my dear students. It means that it is unbounded. So boundedness is leading towards unboundedness. The boundedness is leading towards unboundedness. Okay. The bounded input is leading towards unbounded output, my dear students. The bounded input is leading towards unbounded output. And we don't appreciate this, right? We don't appreciate this. How can we accept this for a stable system? No, it is not at all possible, right? So this system is a unstable system. This system is a unstable system. I gave something which is bounded, I am getting something which is unbounded. I gave something which is bounded, I am getting something which is unbounded, which is not acceptable for us. Acha, can you tell me, can I apply this as an input, my dear students? For checking the stability of the system. For checking the stability of the system, can I apply this? Can I apply the ramp as an input? Please think and tell me, okay? We have already seen similar example before. We have already seen a similar example before. Is it possible? Yes or no? Can I apply the ramp as an input, my dear students? Is it possible to apply ramp as an input? The answer is no. It has to be no, my dear students, because the ramp is an example of a unbounded signal. The ramp is an example of a unbounded signal, my dear students. Yes or no? Ramp is an example of a unbounded signal. So in the first place, I should not apply ramp as an input. In the first place, I should not apply ramp as an input. Why, sir? Because this is against the test of stability. For stability, you have to apply an input which is bounded in nature. For stability, you have to apply an input which is bounded in nature. Then only you can expect an output which is bounded. Then only you can expect an output which is unbounded. You can, if you apply unbounded and you say, sir, I am getting unbounded this year. Here it is unbounded, sir. Here also I am getting unbounded. So it is unstable. No. This is not satisfactory, right? Here you have to apply something which is bounded. Here you have to apply something which is bounded, and you have to expect here bounded. If you are applying unbounded, this is a wrong expectation from your side. It's a wrong expectation from your side, right? So you have to ensure, you have to maintain that this is always going to remain a bounded value. This is always going to be a bounded value. Is that clear to all of you? Y of t is equal to integral minus infinity to t x of tau d tau. Y of t is equal to integral minus infinity to t x of tau d tau. Can you please tell me whether this is a Can you please tell me whether this is a stable system or not? Can you please tell me whether this is a stable system or not? Yes or no? Yes or no? Is it a stable system, my dear students? Please check and tell me. Please check and tell me. Are you able to understand the concepts very clearly? Yes or no? We are yet to reach the gate problems, but we will reach for sure in some time. Let the concepts be very, very clear, crystal clear, then we will be ready for the gate problems, my dear students. And of course, gate problems will make your concept much, much clear. Much, much clear. Very good, Amir, very good. Absolutely correct, my dear Amir. Absolutely correct. If you are giving an input which is u of t, whenever you are integrating the step input, you are going to get an output which is a ramp. You are going to get an output which is ramp. Okay? The integration of u of t leads to the ramp. Now, we know by now this is bounded, so this is fine, but this is unbounded. This is not acceptable. So, we say system is unstable. System is unstable because the step input is leading towards the ramp output. The step input is leading towards what, my dear students? The step is leading towards the ramp. So this is not acceptable for us, isn't it? It is not acceptable for us. Next one is, what is the next one? The next property is linearity. Linearity. It has to satisfy the property called as a superposition principle. Whenever we are talking about a linear system, a system is said to be linear if it satisfies something called as a superposition principle. Something called as a superposition principle. So superposition principle, if it is satisfied, we call the system to be a linear system. Otherwise, we can't call it as a linear system. You remember the example I've given? If you give 1 rupee, you're getting 1 chocolate. If you are putting 10 rupees, you have to get 10 chocolates. That's a simple thing of linearity. As simple as that. So the relation that you have between input and output has to be linear. The relation that you have between input and output has to be a linear. So if I draw between input and output, it should be like this. If I draw between input and output, it should be like this. When x of t is equal to 0, output is equal to 0. So there should be a linear relation that has to exist between input and output. This is what is told by a superposition principle. This is what is told by a superposition principle. What does superposition principle say? Sir, if you give x of t as an input, I'm getting the output as y of t. I'm getting an output as a y of t, yes? Now, if I give a into x of t as an input, then I have to get something called as a into y of t. This is what we call as a homogeneity. Alright, the word is complex, but the concept is very simple. The word is complex, but the concept is very simple. Same thing. 1 rupee, 1 chocolate, 10 rupees, 10 chocolates. Simple. Same thing. This is what we call as a homogeneity or a scaling property. We call it as a scaling property. Next, if I have two inputs, x1 of t and x2 of t applied to the same system. You are applying to the same system. Here you are getting y1 of t. Here you are getting y2 of t. If you are applying input as x1 of t, you are getting y1, x2, y2. Then, if I add these two, my dear students, if I add these two, then it is expected to get the output. If I add these two inputs, it is expected to get the output which is the addition of the outputs, the addition of the individual responses. The addition of the individual responses. Is that clear? Here I am expecting the addition of the individual responses. Addition of the individual responses. This is what we call as a linear system. And this part of it is what we call as additivity. This part of it is what we call as a additivity. This part of it is what we call as a additivity. Yes or no? This is what we call as a additivity. Clear, everyone? Is that clear to all of you? Yes or no? This is what we call as the additivity. Now when you combine these two properties, see in the gate examination this is sufficient. In the gate examination this is sufficient. If you are checking the homogeneity, it is sufficient in the gate examination. But as a superposition principle, you expect what? If x1 is leading to y1, x2 is leading to y2, then a into x1 of t has to lead to what? A into x1 of t has to lead to a into y1 of t. Let me call it as a1, and here b1 into x1 of t, x2 of t. Simply I can call it as a also, no problem. Okay. So b into x2 of t has lead to b into y2 of t. B into x2 of t has to lead to b into y2 of t. If this is satisfied, then we call the system as a linear system, and this is what we call as a superposition principle. And this is what we call as a superposition principle. But I told you already, in the examination point of view, it is sufficient to check the homogeneity. For example, let us take an example here. Y of t is equal to 2 into x of t plus 3. Y of t is equal to 2 into x of t plus 3. Y of t is equal to 2 into x of t plus 3. Can you please tell me whether it is a linear system or not? We are very tempted towards calling it as a linear system because it looks like a line, isn't it? It looks like a line. Can we call it as a linear system? Can we call it as a linear system? Yes or no? Yes or no? No. Harsha says it's non-linear. Harsha says that it is a non-linear. What about others? Amartya also says it is non-linear. Amartya also says it is non-linear. Come on. Yeah, very good. I think everyone says it is non-linear. Very good. It is simple, right? If I give input as x of t, what is the output? What is the system doing here? Just try to understand what the system is doing here. The system is multiplying my input with 2 and adding 3 to it. What is the system doing here? The system is multiplying my input with 2. The system is multiplying my input with 2 and it is adding 3 to it. Whatever input you are giving to the system, the system is multiplying that with 2 and adding 3 to it. So even if I stand here, even if I'm standing here, what is the system doing here? The system is multiplying me with 2 and adding 3. This is what the system is doing here, my dear students. This is what the system is doing here. Now, can we call this operation as a linear operation? Can we call this operation as a linear operation? Yes, I can completely understand. This is y is equal to mx plus c, so it has to be linear. But let us see that why it is not. Let us see that why it is not. Okay. So when I give an input which is a into x of t, then when I give an input which is a into x of t, then what are we going to get? I told you, whoever stands here, this is going to be multiplied with what? 2. This is going to be multiplied with 2. Whatever is there here, this is going to be multiplied with 2 and 3 is added to it. And 3 is added to it. So it has to be 2a x of t plus 3. This has to be, when you're passing through the system, it will be what? 2a x of t plus 3. But is this equal to a into y of t? Is it equal to a into y of t? Is it equal to a into y of t? Please check. A, y of t, what is y of t? Y of t is nothing but, here it is given, right? 2 into x of t plus 3. So it is 2a x of t plus 3a. 2a x of t plus 3a. This is a into y of t. What is this? This is a into y of t. A into x of t is not equal to a into y of t, because a into x of t is leading to what? To a x of t plus 3. It is leading to 2a x of t plus 3, but it is not leading to a into y of t. It is not leading to a into y of t, my dear students. That is a problem. Understood? Is that clear, my dear students? Is that clear, everyone? Okay. Can you try with y of t is equal to, So now how can I make this system a linear system? How can I make this system a linear system? What if I remove 3? What if I remove 3? Now it is fine, right? If I just remove this 3, then it is fine. What does it mean? What does it mean? As Ranjit is rightly telling, it is still a line, right? The relation between x of t and y of t is still a line. The relation between x of t and y of t is still a line. Something like this. But the problem is that when your input is 0, the output is something which is non-zero. It means that you're not giving any input, or you're giving an input which is 0, but still the output is available, which is against the linearity, my dear students. It's like you didn't put that rupee, you're still getting chocolate. You didn't put that rupee, you're still getting the chocolate, right? This is not acceptable. Okay, so this is an offset. This is what we call as an offset. Okay, this is available. This is the problem. This is the reason why it is non-linear. We don't expect this from a linear system. We don't expect this from a linear system. Okay. Now let us say y of t is equal to mod of x of t. Y of t is equal to mod of x of t. Is it a linear system? Y of t is equal to mod of x of t. Is it a linear system? Yes or no? Is it a linear system? Yes or no? Is this a linear system? Y of t is equal to mod of x of t? Yes or no? No. No, sir, because you see the relation. We expect a linear system to be like this, right? Simple. But how to do it with the help of the superposition principle? How to do this with the help of a superposition principle? Can you try? Okay, graphically yes. Graphically there is some problem with this, right? But mathematically, can we try? I am giving input as x of t, passing through the system, it is giving me y of t. What is y of t, my dear? What is y of t here? Y of t is nothing but the magnitude of x of t. Y of t is nothing but the magnitude of x of t. It is nothing but the magnitude of x of t. It means whoever is standing here, it is just going to give the magnitude of it. The same person magnitude. If I give a into x of t as an input, if if I give a into x of t as an input, I'm going to get the output which is which means that it is mod of a mod of x of t. Mod of a times that of mod of x of t. Mod of a times that of mod of x of t. Now, is this equal to a into y of t? Whatever I give here, the magnitude of this will come here. Now, is it equal to a into y of t? No, because this is a into mod of x of t. If a is negative, then there is a problem. If a is equal to -1, here it is -1 mod, which is 1, mod of x of t. Here it is -1 times that of mod of x of t. There is a problem. There is a problem. So when the value of a, someone says, sir, a is equal to 1, then it is satisfying, sir. A is equal to -1, it is not satisfying. For a is equal to 1, it is satisfying. No, it cannot be like that. A can take any value. A has to take any value, but still it has to be applicable. But here in this case, if a is the negative number, then it is not applicable. Then it not comes to be a linear system. A is something that can be a real value or a complex value. A is something that can be a real value or a complex value. You have the liberty of taking, you have the freedom of taking any possible value of A. You have a liberty of taking any possible value of A, okay? If it satisfies for any possible value of A, then only I can call it as a linear system. But here the problem is that it is not satisfying for a negative value of A. It is not satisfying for a negative value of A, so I cannot call the system as a linear system. I have to call it as a non-linear system. I have to call it as a non-linear system, okay? I have to call it as a non-linear system. Next example, next property, the last property. Time invariant and time variant systems. Time invariant, time variant systems. Time invariant, time variant systems. I think we have already discussed, my dear students, yes or no? We have already discussed this. We have already discussed this, that if I am calling a system as a time invariant system, if I am calling the system as a time invariant system, it means that the behavior, the characteristic of the system should not change with time. Yes or no? The characteristic, the behavior of the system should not change with time. Right? Then we call the system as a time invariant system. Then we call the system as a time invariant system. So please bookmark the GATEvantage series schedule. It will be very, very helpful for you. Okay. So time invariant, time variant system. Time invariant, time variant system. If behavior of the system is not varying with time, if behavior of system is not changing with time, there are some very, very important points in this concept. Okay. If you know those important points, you can directly solve the problem. Most of the cases, you will directly solve the problem if you know those important points. So if the behavior of the system is not changing with time, then it is a time invariant. We call it as a time invariant system. So how do we say this in a mathematical manner? How do we say this in a mathematical manner? How do we say this in a mathematical manner? Very simple. If I say that x of t gives you y of t. Okay, I am giving an input. I am giving an input x of t, I am getting an output y of t. If I give the same input after 10 days, I am giving the input x of t, I am getting the output y of t. If I am giving the same input after 10 days, then I have to get the same output not today, after 10 days. Okay, if I am giving the same input after 10 days, meaning what? If I am giving the same input after 10 days, meaning what? So let us say there is a step, I am giving a t equal to 0. Okay. Now I wanted to give the input after 10 days. I wanted to give this input after 10 days. It means that I am giving the step at t is equal to 10. Just an example, okay? I am giving the step at t is equal to 10. So there is a shift in 10 days. It means if I am delaying the input by 10, if I am delaying the input by 10, it means I have to get the same output. I have to get the same output when? After 10 days. It means that this has to be y of t minus 10. So in general we can say, if the system is time invariant, x of t gives y of t, then x of t minus t1 has to give you y of t minus t1. X of t minus t1 has to give you what? It has to give you y of t minus t1. If this is satisfied, then we can call the system as a time invariant system. Then we can call the system as a time invariant system. Okay. The delayed input is leading to delayed output. The delayed input is leading to delayed output. We can call the system as a time invariant system. This is how we mathematically approach it. We understanding point of view, behavior of the system does not change. If x of t leads to y of t today, after 10 days, the same x of t has to lead to y of t. The same x of t has to lead to y of t after 10 days. Now there is a simple process of doing this. First, what you will do mathematically, whenever you are wanted to find whether it is a time invariant system or not, you will follow a very simple process. What is that? First, you will find out what is y of t minus t naught or a t1, whatever it is. Okay. Let me call it as a, chalo, no problem, doesn't matter. Y of t minus t1 I will find out. Second thing, I will consider what? I will consider that let x of t minus t1 be equal to x1 of t. This is a general process, but I will give you a simple observations. Okay, directly you can put observations. Most of the cases you will get the correct answer. Okay, third one. If I give input as x1 of t, the output has to be y1 of t. Fourth one. Now you check whatever output y1 of t you got, whether this is equal to y of t minus t1 or not. If this is correct, then it is a time invariant system. If this is correct, it is a time invariant system. If it is not correct, then it is a time variant system. First thing what we are doing, we are finding out what is y of t minus t1. Second thing what we are doing, we are just trying to do some makeup to this x of t minus t1. We are just trying to do some makeup as a x of t minus t1 as what? x1 of t. Now if I give input as x1 of t, the output I am getting is y1 of t, passing through the same system. X of t gives y of t. Okay, x1 of t leads to y1 of t. Now I will check, hold on, this is x of t minus t1, right? This is x of t minus t1. It means that it has to be y of t minus t1. If y1 of t is equal to that of y of t minus t1, I will call it as a time invariant system. Simple example. Y of t is equal to t into x of t. I am taking this, okay? Y of t is equal to t into x of t. Now first thing that I am going to do is that I will find out what is y of t minus t1. Y of t minus t1 is equal to t minus t1 times that of x of t minus t1, right? Because wherever there is a t, I am replacing it with that of t minus t1. Wherever there is t, I am replacing with it of t minus t1. So here also there is t, I am replacing with t minus t1. Here also there is t, I am replacing with t minus t1. So I found out what is y of t minus t1, number one. Number two, what? X of t minus t1, I am going to call it as a x1 of t. Third step, if I give x1 of t as an input passing through this system, the same system, passing through the same system, the output is y1 of t. Now tell me, what is y1 of t? What is y1 of t, my dear students? What is y1 of t? What is system doing here? What is the system doing here? If I am giving an input called as x of t, the output of the system is nothing but the same x of t just multiplied by t. It means that whatever is the input, the system is multiplying the same input with that of t. Here also if you see, the input here is x1 of t. So what the system is going to do? The system is going to multiply the same input x1 of t with that of t. It is just going to multiply the same input x1 of t with that of t. This is t, x of, what is x1 of t? X of t minus t1. What is x1 of t? It is x of t minus t1. So here it is t times that of x of t minus t1. I repeat once again, first thing is that we will find out what is y of t minus t1. What is y of t minus t1? T minus t1, just replace t with t minus t1, t minus t1, t minus t1. Now I am just considering x of t minus t1 as x1 of t. Okay, here x1 of t is leading to what? y1 of t. What is y1 of t? If x of t leads to t into x of t, x1 of t has to lead to t into x1 of t. If x of t leads to t into x of t, x1 of t has to lead to t into x1 of t, right? So t times the of, what is x1 of t? x1 of t is nothing but x of t minus t1. X of t minus t1, right? Yes or no? So this is not equal to the of y of t minus t1. That is the problem here. It is not equal to the of y of t minus t1. It means this is a time variant system. Is there a shortcut, sir? Yes. There is a shortcut. What is that? What is that? Please write down. These are some very, very important observations. Some very, very important observations. Number one, whenever you are having y of t is equal to some function of time multiplied by your input. Whenever you are having the output which is some function of time multiplied by the input, by some function of time multiplied by the input, then this system is a time variant system. Directly I can say. Example, t into x of t, some function of time multiplied by x of t. Any other example? Y of t is equal to sin t times that of x of t. Y of t is equal to log t multiplied with that of x of t. So whenever you have these cases, the system is going to be time variant in nature. Second thing, the time reversal is a time variant operation. The time scaling is a time variant operation. The time scaling, when you have a scaled output, when you have a time reversed output, these are time variant operations. These are time variant operations. What about time shifting? Direct observations, Direct observations you can try with the same process. If you are having any doubt, you can try with the same process. You will get these to be a time variant systems only. You will get this to be a time variant systems only, okay? You will get these to be a time variant systems only. What about a simple integrator? What about a simple integrator if I am writing here? Important points. A simple integrator is also an example of a time invariant system. It's an example of a time invariant system. Time shifting is an example of a again a time invariant system. Okay, it's also an example of a time invariant system. These are some very, very important observations. Y of t is equal to f of t times that of x of t. Y of t is equal to f of t times that of x of t. It's a time variant operation. Examples: time reversal, time variant operation; time scaling, time variant operation. But a simple time integrator is a time invariant operation. That is time variant, this is time invariant. Here Simple shifting is an example of a time invariant operation. Thanks a lot, Yashwant. Thank you. Here it's a time invariant operation. Is that clear, my dear students? Is that clear? Everyone? Is that clear? Yes. Next. Is that clear to all of you? Very nice. Let us start solving the gate problems now. Okay? Let us take another half an hour, 40 minutes to solve the gate problems. I hope you don't mind. I know we are very close to the top, 10 o'clock, but if you can give another 15-20 minutes extra or a half an hour extra, we can solve more problems. We'll try to cover different models of the system properties. Okay? Another half an hour of patience will really help. Another half an hour of patience will really help us. Okay? So now tell me, you are having y of n is equal to sine of 5 pi by 6n multiplied with that of x of n. Sine 5 pi by 6n multiplied that of x of n. Sir, I missed the signals and system subject due to lockdown. So is it easy for me to solve the problems in gate 22? If you are practicing, if you are attending classes, then definitely it is possible. Okay? You please try to cover it up. You please try to cover it up. It is definitely possible. Okay? It is one of the scoring subject, no doubt about it. It is definitely possible. So here the question is all about the linearity, stability and invertibility. I told you, right? Whenever the gate asks the question, it is a group of properties. It is not a single property, it is a group of properties. Now the good thing is that we have already covered all the properties. Now we are ready for the problem solving. Now we are ready for the problem solving. Y of n is equal to sine of 5 pi by 6n into x of n. Into x of n. First let us talk about the linearity. If I give input as x of n, what is the output? If I give input as x of t or x of n for that matter, what is the output? Output is y of n. What is y of n? Y of n is nothing but x of n times that of some sine function, right? X of n times that of sine function. So what the system is doing here? The system here is multiplying your input with that of sine function, nothing else. The system here is multiplying your sine function with that of, your input with that of the sine function. So what if I'm having an input called as a into x of n? What if I'm having an input called as a into x of n? Then it is going to be what? A into x of n is an input. A into x of n is an input. Now this input is multiplied with a sine because that is the property, right? That is what the system is doing. Whatever input you give, it is going to be multiplied with sine. Whatever input you give, here the input is a into x of n, the same input is multiplied with it of sine. Now isn't it equal to a into y of n? Isn't it equal to a into y of n? Definitely yes. It is definitely equal to a into y of n. It means that the system is linear. The system is linear. The system is linear. Is it stable? Definitely yes. Definitely yes, it is stable. Why, sir? Input is x of n, the output is y of n. What is output? Output is nothing but x of n multiplied by some sine function. Is the sine function bounded function? Is the sine function a bounded function? Sine, simply speaking, it oscillates between 1 and minus 1. It just oscillates between 1 and minus 1, right? So it's a bounded function. And when you're checking the stability, even this is bounded. Bounded input leads to bounded output. Bounded input leads to bounded output. So you have to ensure that your input is bounded in nature. You have to ensure that your input is bounded in nature, right? That is how you check the stability of the system. You have to ensure that your input is a bounded in nature. So bounded leads to bounded. Bounded input multiplied by bounded function leads to bounded output. So both are bounded. It means that the output is also bounded. It means bounded input leads to bounded output. The system is stable. This is correct. This is correct. Now what about invertibility? What about invertibility? What about invertibility? Let us say I'm giving an input called as del of n. The output is del of n times that of sine phi pi by 6n. Del of n multiplied with that of sine phi pi by 6n. Can you please tell me what is f of n multiplied by del of n? This is a very important property that we studied in the first chapter. Whenever you are multiplying the impulse with it of the input, any function, then where is the impulse? The impulse is present at n equal to 0. So you are going to get f of 0 multiplied by del of n. This is the nature of it. Here the impulse is present at n equal to 0. So you are going to get the sample of the function at n equal to 0. Wherever there is an impulse, there you are going to get a sample of the function multiplied with the of del of n. Multiplied with the of del of n. Okay. Okay. So this is the property. So this is going to be, if I put n equal to 0 here, this is going to become 0. This is going to become 0. Okay. So I am giving some input, the output is becoming 0. From 0, can you extract the input back? Is it possible for you to extract back the input? The output has become 0 now. For a non-zero value of input, the output has become 0. Is it possible for you to extract back the input? Not possible. That is one way of saying it is non-invertible. That is one way of saying, because it is not possible, right? From 0, what you can extract? From 0, nothing can be extracted back, right? The other way of saying is that, let me apply del of n minus 6 as an input. It's a different input, isn't it? Del of n minus 6. Even though it's a delayed input, we'll consider it as a different input. Then what is the output going to be? The output will be del of n minus 6, whatever input you are having, multiplied by sine of phi pi by 6 multiplied by n. Sine of phi pi by 6 multiplied by n. Now, where is the input? Where is the impulse? The impulse is present at n equal to 6. If I substitute n equal to 6 here, if I substitute n equal to 6 here, the impulse is present at n equal to 6. We discussed in the class, I can directly substitute n equal to 6 here, right? In the classroom, we have discussed what? If I am having f of n multiplied by del of n minus n1, f of n multiplied by del of n minus n1, then this is equal to f of n1 multiplied by del of n minus n1. We discussed that it is nothing but f of n1 multiplied by del of n minus n1. So if I directly put 6 here, then this becomes what? Phi pi. Sine pi, phi pi is what? Sine phi pi is 0. So del of n gives you 0. Del of n minus 6 is also giving you 0. Del of n is giving you 0 and del of n minus 6 is also giving you 0. It means that the system is non-invertible. Two different inputs lead to the same output. Two different inputs are leading to the same output. Two different inputs are leading to the same output. So here we have used the property of impulse. To solve this problem, we have used the property of impulse. What does it say? F of n multiplied by del of n is f of 0 multiplied by del of n. F of n multiplied by del of n minus n1 is going to be f of n1 multiplied by del of n minus n1. Let me write it again. F of n multiplied by del of n minus n1 will be equal to what? Where is the impulse? The impulse is present at n equal to n1. So I'm going to get the sample of this function at n1. I'm going to get the sample of the function at n1 multiplied by what? Del of n minus n1. Del of n minus n1. Is that clear? So if I substitute like that, I am putting n equal to n1 here. Here I am putting what? N equal to 6. The impulse is present at n equal to 6. So I am substituting it here. So this becomes what? Sine of phi pi. Sine of phi pi is nothing but equal to 0. So two different inputs I am having the same output. Two different inputs I am having the same output. It means that the system is non-invertible in nature. It means that the system is non-invertible in nature. So it is linear? Yes. Is it stable? Yes. It is non-invertible in nature. Option C is the correct answer. I think Harsha has answered it correctly. Amartya is also answered it correctly. Very good. Harsha and Amartya both have answered this correctly. Very good. Very good, my dear students. Next question. Next question. This is a recent question. Fresh. This is a fresh question for us. And the question is about the linearity and time invariance. The question is about the linearity and time invariance. Who can answer this correctly? Please read the question. Okay. and try to answer this properly. Try to apply the concept, whatever concept we have learned, please try to apply the concept. Please try to apply the concept. Okay. Y of t is equal to max of 0 comma x of t. Y of t is equal to max of 0 comma x of t. I think Anuj has answered it as B. Amartya has answered it as B. Okay. Please try to understand this. Let us say x of t is equal to 1. Let us say x of t is equal to 1. Then what is the output? Max of 0 comma 1 is 1. If x of t is equal to 2, max of 0 comma 2 is 2. If x of t is 3, max of 0 comma 3 is 3, right? Yes or no? Yes or no? So how can I draw this? How can I draw this? How can I draw this, my dear students? If x of t is 1, let me say this is t, this is x of t. I'm sorry, this is x of t and this is y of t. I'm really sorry. This is x of t and this is y of t. Okay. So what can I say, my dear students, here? What can I say? If x of t is positive, if x of t is positive, then it is going to be what? The same value. Y of t will be equal to x of t. If x of t is positive, if x of t is positive, then y of t is equal to x of t. If x of t is negative, if it is minus 1, if it is minus 2, then what will happen? If this is minus 1, max of minus 1 comma 0 is what? 0. Max of minus 2 comma 0 is what? 0. It means that in the other hand it's going to be like this. On the other hand it is going to be like this. Yes or no? On the other hand it is going to be like this. Now what about time invariance? What about time invariance? What about time invariance? Have you checked the time invariance, my dear students? Have you checked the time invariance? See, this is the plot. The plot is not like this. The plot is not like this. This is linear. This is non-linear, right? Because if your x of t is negative, it is not following your input. If x of t is negative, it is not following your input. It is simply 0. Right? So this is a non-linear system. This is a non-linear system. What about time invariance? How to check the time invariance? First of all, find out what is y of t minus t1. Find out what is y of t minus t1, max of 0 comma x of t minus t1, right? 0 comma x of t minus t1. Y of t minus t1 is equal to max of 0 comma x of t minus t1. This is nothing but y of t minus t1. This is nothing but y of t minus t1. The second one. let x of t minus t1 is equal to x1 of t, is equal to x1 of t. Third, if I give x1 of t as an input, then what is the output, my dear students? If I give x1 of t as an input, then what is the output, my dear students? It is max of, to put it simple, this is nothing but y1 of t, right? If I give x1 of t as an input, if I give x1 of t as the input, what is the output going to be? Doesn't matter, it is nothing but max of 0, x1 of t. Max of 0, x1 of t, which is nothing but max of 0, x of t minus t1. This is nothing but y of t minus t1. This is nothing but y of t minus t1. Okay, this is nothing but y of t minus t1. Okay, so thereby y1 of t is equal to y of t minus t1. y1 of t is nothing but y of t minus t1. So thereby the system is time invariant and the system is non-linear. The correct answer is non-linear and time invariant. Okay, so if you are liking the channel, if you wanted to follow the GATEvantage series, please subscribe to the channel. Okay, and don't forget pressing the bell icon. Okay. Okay. So is that clear to all of you? 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 Next question. The students who did not take it up, please take the screenshot of this. If you're having any doubt, please ask me. If you're having any doubt, please ask me. But I think it's very clear. If you know how to plot the relation between x of t and y of t, you can comment on the linearity. And this is the process that we have discussed about time invariance. If you follow this, you will understand why it is time invariant. Now, this is a very simple question if you have followed the linearity. This is a very simple question if you have followed the linearity. Again, it's a recent question only, not a very old question, it's a fresh question. Is there any chance to extend the series? What do you mean by extending the series? Are you interested to learn more number of concepts? Is that what you're trying to say? See, if you have attended the concept where we have discussed linearity, you can easily solve this problem. You can easily solve this problem. The only change is there that input here is mentioned as u. The input here is mentioned as u. The input here is mentioned as u. Option A is nothing but, it's a differential equation. Option B is given as y of t is equal to integral 0 to t e power a t minus tau b u of tau. Option C is given as y is equal to au plus b. Option D is given as y is equal to au. We already know that y of t is equal to a into x of t is a linear system, and we already know that y is equal to a into x of t plus b is a non-linear system, especially when b is not equal to 0. Especially when b is not equal to 0, and the question is only to find out what is a non-linear system. The question is only to find out what is a non-linear system, isn't it? The question is not to find out what is a linear system. Please understand, this is where students do mistakes. They see the word linear, no, I'll solve this. You have to read the question very clearly. The system is about non-linear, okay? And you know that y is equal to a into u, y is equal to au plus b is nothing but a non-linear system. So this has to be tick marked. Now this also offers us one very important thing. This equation in mathematics, You please check in mathematics, this is what we call as a linear constant coefficient differential equation. This is what we call as a mathematics, if you remember, this equation is what we call as a linear constant coefficient differential equation. We call it as a linear constant coefficient differential equation. A linear constant coefficient differential equation in signals becomes an LTI system, linear time invariant system. You have to mark it up. You have to mark it up. You have to mark it up. Linear constant coefficient differential equation is nothing but a linear time invariant system. Is nothing but the linear time invariant system. Okay, and you can check remaining both. It will satisfy linearity. Remaining both of them will satisfy linearity. Remaining both of them will satisfy linearity. Next question. We'll solve one more problem, okay, after this. Okay, so a system with input x of t and output y of t is defined by input-output relation. Come on, a system with input-output relation is defined by y of t is equal to integral minus infinity to minus 2t x of tau d tau. X of tau d tau. Now this system is what? This system is causal, time invariant, unstable. Causal, time invariant, unstable. Causal, time invariant, stable. Non-causal, time invariant, unstable. Non-causal, time variant, unstable. Can you please tell me what is this? Can you please tell me what is this? First of all, let us talk about causality. Let us talk about causality. When I put t is equal to minus 2, if I put t is equal to minus 2, then y of minus 2 is equal to integral. It is equal to integral minus infinity to what? T equal to minus 2 if I put, then this is nothing but 4 x of tau d tau. Now you see, please try to understand. Please try to understand. If I wanted to get the output at t is equal to minus 2, I have to integrate my input till 4. I have to integrate my input till 4. If I have to get the output at t is equal to minus 2, I have to integrate my input till 4. This is non-causal, yaar. This cannot be causal. This cannot be causal. This has to be non-causal. Next, if I just have the difference between time invariance, I can directly answer the question. See, I discussed you that y of t is equal to f of t multiplied by x of t. Y of t is equal to x of t, f of t multiplied by x of t is a time variant system. Time scaling operation is a time variant system. Time reversal is a time variant system. Now you see here, you are multiplying your t, even though it is an integrator. Even though it is an integrator, yes, it is an integrator, but the problem here is that you are multiplying this t with the of minus 2. It means that you are scaling it. You are applying minus, it means that you are reversing it. You are applying 2, it means that you are scaling it. You are scaling the time and you are reversing it. Had it been a very simple integrator, had it been a very simple integrator like this, had it been a very simple integrator like this, my dear students, it's a time invariant system. But because of the fact that you are multiplying it with 2 and you are multiplying with minus, it means that you are scaling it and you are reversing it. This system will be a time variant system. This system will be a time variant system. Why, sir? Because you are scaling it, you are reversing it. Because you are scaling it and you are reversing it, that is why this is a time variant system. The system is non-causal time variant system. The system is non-causal and time variant system. Non-causal and time variant system. Okay? Clear, everyone? See, if you practice enough, and you can just look at the question and answer, most of the questions which is belong to system properties, you can just look and answer if you have practiced enough. If you have practiced enough, okay? Next question. Last question for the day. 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 So whenever you are having an integrator, what did we discuss about stability? I'm sorry. Whenever we are having an integrator, what did we discuss about stability? Whenever we have an integrator, what did we discuss about stability, my dear students? What did we discuss about stability when we have an integrator? Whenever you are having an integrator, the system is unstable. Whenever you are having an integrator, the system is unstable. And when you are multiplying your input with some function of time, when you are multiplying your input with some function of time, the system is time variant in nature. Time variant in nature. It's not a time invariant system. It's not a time invariant system, and it is unstable. The answer is option D. It is unstable because it's an integrator. Whenever you are having an integrator, it's an unstable system. Second thing is that you are multiplying your input with some function of time. You are multiplying your input with some function of time. It is going to become a time variant operation, or it is not a time invariant operation. Is that clear? Right, so we have more problems, but I think we have running out of time. So today we are not doing live quiz, my dear students, okay? Today we are not doing live quiz. I would be wanting all of you to revise a little bit more, to do problem solving on this, and tomorrow, believe me, we will definitely do the live quiz of both convolution and also the system properties. Together we'll do the live quiz of both convolution and the system properties, okay? Tomorrow probably we will extend the session till 10:30. Okay? Tomorrow we will probably extend the session till 10:30, and we will have the last half an hour to be a live quiz, complete out and out live quiz session for tomorrow. Okay? So first 2 hours we'll be discussing about the concept of convolution. The next half an hour we'll do the live quiz, which is a combination of the system properties and the convolution. Yeah, it is asked in my examination. Hey, very nice. So how does the integrator be unstable? That is what we discussed earlier. We discussed earlier that when you give the input as u of t, then what is the output? If the integration of u of t is what? Ramp. The integration of u of t is ramp, isn't it? Yes or no? The integration of u of t is ramp, isn't it? And ramp is unbounded. This is bounded. Boundedness is leading to unboundedness, right? Boundedness is leading to unboundedness. It means that it is an unstable system. It means that it is an unstable system. Is that clear to all of you? Is that clear to all of you? Okay. Cool, my dear students. So wish you good night, sweet dreams, but do practice. Okay, this is a very, very important time for all the GATE aspirants. It's a very, very important time for all the GATE aspirants. You have to be charged up. You have to put a lot of energy into your preparation. Once you do that, I'm sure the success will come to you. The success will come to you if you are doing your job in a very good manner. As of now, your job is to focus completely on the GATE examination and ensure that you are doing more and more problem solving. Okay? So I believe you didn't have your dinner. Okay? So please have your dinner and then sleep well. Okay? Wish you all the very best, my dear students, and see you tomorrow at 8 p.m. We will discuss about the concept of convolution. Again, it's a very, very important concept. Right? Wish you all the very best. Bye-bye. Good night.